So, okay, as mentioned just now, material removal rate is very important in any manufacturing process, because actually that shows the efficiency of the process. That will determine whether the process is viable for your operation or not. So in MC, material removal take place due to atomic dissolutions of the workpiece. So you can actually calculate the material removal rate in this particular process using these particular equations. So MRR is equals to this is M is mass of the material dissolved divided by T is equal to time period of the process, and P is density of the material. So this is will be can be extended into this, where I is the current, A is atomic weight. So this is atomic weight of the materials that's being dissolved. This is workpiece material atomic weight, right? So current times the atomic weight divided by F. F is basically a Faraday constant. So Faraday constant is 69,500 coulombs times the density of the materials times V, which is the valency. So V is basically, valency is the available electrons for reactions of the both workpiece and also the tools materials of the workpiece materials. So based on this equation, then you can actually calculate what is the MRR for that particular process going to be. Yeah. Again, if you have any question, just ask me. So this is the examples of the calculations for it. So I'm not going to go through it. There's a solution in it. Okay. So advantages of this particular process. One is there's no cutting forces. Therefore, clamping is not required except for controlled motions of the workpiece. So basically, there's no cutting force. There's no contact between the workpiece and the tools. Therefore, the clamping is not required except for the controlled motion of the workpiece, except if you want the workpiece to move relative to the tools. Right? That's it. Second, it can be machined. It can machine configuration which is beyond the capability of conventional machining process. So in terms of this, basically it's referring most often than not to the surface finish, because again, as mentioned just now, it's actually machining at the atomic level, So you can achieve very good surface finish using this particular process, right? And also there's no stress involved in it, so you can get a finished goods without any build-up stress in it. So there's no warpage, so on and so forth. Very accurate. You're talking about tolerance of about plus or minus 0.2 mm. This is relatively fast. So this is faster than EDM process actually. Most often than not, most often than not, is can be faster than the EDM process. Can machine harder metals than the tool. So you can machine harder metals than the tool. So the tools can be copper. You can machine hardened steel using this particular process. So this is just like when we talk about the EDM process. Extremely thin materials can be easily worked without distortion. So just imagine if you want to machine a very thin workpiece, the thing that's very difficult to control in machining thin material is deformations of that particular material itself due to physical contact or due to build up in internal stress. But for this particular process, that does not matter, because there is no physical contact between the two, and materials being removed at atomic level. and you can get a very good surface finish. You're talking about 0.2 to 0.8 micron. So this is very, very good surface finish. Some disadvantages: high energy consumption. So your electrical bill will be high using this particular process. Again, mentioned just now, is a low voltage, high current process. So it's a high energy consumption. It cannot machine non-conducting material. So non-conducting material cannot machine with this. Corrosion or rust of EMC machine can be hazardous, but preventive measure can help in this regard. So basically, uh, because of the chemical reactions, the EMC machines is subjected to rusting problem. So so you have to use proper procedures, so on and so forth, to protect the machine itself. Initial tooling can be time consuming and also costly. So initial toolings, so because you have to fabricate the toolings itself, so you have to machine the tooling to make to machine the workpiece. So that takes time and also cost. Environmentally harmful byproduct. So this is chemical reaction. So just now you tend to have some chemical effluents out of this particular process. So you have to you have to have a system in place to take care of those byproducts. Some design considerations for EMC. So knowing the advantages, disadvantages, what EMC can do. So these are the things that you need to think of before you start designing your product to be machined using this EMC process. So it says here, the tendency of electrolyte to erode away sharp profiles, electrochemical machining is not suitable for producing sharp corners or flat bottom. So your end product, if you want your end product to have a sharp corners or a sharp profiles, you won't get it within EMC process, because in the EMC process, it tends to erode away sharp profiles, because whenever you have a sharp profile, then basically that's the easiest way for the chemical reactions to happen. So because when you have chemical reactions, it has something to do with the surface energy. So whenever you have a sharp profile, then surface energy for that particular area becomes very high. So because of that, then the sharp surface, feature, surface, and so forth, will be the first to erode. So basically, if you want to design a part that must have a sharp profiles, then EMC is not one of your process that you should consider. Okay. Controlling the electrolyte flow may be difficult, so irregular cavities may not be produced to the desired shape with acceptable dimensional accuracy. So if you want a cavity with irregular cavities, for example, if you want to do this particular process to machine a surface like a coin, right? So if you have a surface of the coin, there are a lot of features in it, right? So you have a lot of irregular cavities. So using EMC process, then you won't be able to get that particular feature, right? So so because of that, then basically if that's what you want to have, you're going to have a final product which has a lot of irregular cavities, so on and so forth. You might not get that at the end of the process. Design should make provision for small taper for holes and cavities to be machined. So when you design your parts, your final product, if you have a hole, then the hole will have a taper. It will not be a straight hole. So you have to make that provision. Make sure that you design a product, then you should envision that you should expect that the product produced using EMC process will have a taper hole. Yeah. The shape tools should be either in the form of solid or tubular form and generally made of brass, copper, bronze, or stainless steel. So the shape tools should be in the form of solid or tubular form. So it should be a for solid or a tubular form. Uh, I didn't do that. Did I? I'm not sure what happened there. And generally made of brass, copper, bronze, and stainless steel. The accuracy of the tool shape directly affect the workpiece accuracy. So the accuracy of the tool shape, directly affect the workpiece accuracy. So if your tools is not uh, accurate, then the workpiece will the machine's surface will not be accurate either. Okay. Any questions? Any questions? Okay. Okay. Applications of EMC process. The main application of EMC process are in machining of hard heat resistant alloy. So if you have alloy that which is hard and heat resisting alloy, right? Uh, Usually it's very hard for you to machine using this particular process, using a conventional process. So those kind of workpiece is suitable for EMC or for cutting cavities in the forged dies. So during forging process, you have to make the dies, and to make the dies, the die is made from the very hard and heat resistance alloy, steel usually. So basically, this particular process is suitable for that, yeah, making cavity on the forging, or drilling holes, or machining of a complex internal shape like that of a turbine blades. So if you want to machine a complex external shape, like a turbine blades. So if you look at the turbine blades for the aerospace component, uh, I'm not sure why the highlighting is there. Maybe somebody else is doing that. Anyway, so so the turbine blades, aerospace component, which are tungsten carbide, and that of nozzle of alloy steel. So basically, whenever you're dealing with hard alloys, the complex external shape that you want to make, like turbine blades. So turbine blades, just imagine turbine blades. You have a very very complex contour of the flat contour of the turbine blades, right? So it's very hard for you to machine it. So EMC can do that. And almost any conducting materials can be machined using these particular methods. Uh, it is also used for machining and finishing forging die cavities, die sinking, and to produce small holes. So EMC also be known to be used for this particular process, whereas it's being used for the uh, for the making this finishing forging dies cavity, die sinking, and to produce small holes. So if you want to produce small holes, and finishing on the forging die cavities. So forging, as mentioned just now, forging die. If you want to do forging operations, you want to forge using a tool. So you have to make a tools, and that tools, the surface qualities must be very very important. So if the surface quality is not good, then during forging process, we transfer that surface quality into the workpiece. These examples of the micro holes we machined using a different fit rate. So this is a micro holes machined using different fit rate, and you can look at the effect of it. So this is A, So this is at 10 microns per second feed rate. This is 0.2 microns per second. So feed rate actually have an effect to the surface finish of the holes. More recent applications of EMC include micro machinings of the electronic industry. So recent applications, EMC also, ECM also being used for micro machining for electronics industry applications. So this is one of the examples of it. If you want to make a hole on, let's say, for example, copper layer, you want to make a hole. So copper layer, this is usually is very thin. So you don't want to induce stress on it. So EMC, ECM is one of the process that they can do that. This is 3D micro cavity fabricated by different machining conditions. So on the left hand side, this is by EDM process. So if you look at EDM process, you look at the surface layer of it. So this one is using SEDCM process. So SEDCM stands for simultaneous electro discharge chemical machining. So this simultaneous electro discharge and also chemical machining process. So if you look at the two, you can see the surface finish that can be achieved using electrochemical machining process. Right? Much better compared to EDM process. So that's basically the materials I would like to cover today. Is there any questions? We have plenty of time for question and answer if you have any questions. No?
Sir,
Yes.
untuk midterm masuk sampai chapter berapa, sir?
Untuk midterm, dia akan masuk sampai chapter topic before semester break. Nanti saya akan confirmkan. Saya akan confirmkan and then let you know. Basically, it's a topic before kita punya semester break, kita punya official semester break. Kalau you tengok on the kita punya apa tu? Kita punya teaching plan in the ULEN, right? So those topics covered before the semester break is covered in the midterms exam. Am I answering questions?
Okay, sir.
Alright. Any other question? Actually, midterm question dah siap, tapi kami kena revise balik. Sebab it's going to be a open book exam. So we need to revise the questions again. So I think we're going to design the open book questions to last for about 6 hours. About 6 hours. So you have 6 hours to answer the questions and upload the answer on in the system, roughly. So because of that, then we have to change the questionnaire. Questionnaire will be a bit more complex. Any questions? I'm going to upload the second assignment. So first assignment, you guys are doing it right now. So because we have not done ultrasonic yet. I'm going to upload the second assignment in the week 10 lecture. So watch out for that assignment. That assignment is basically focusing on one topic only, which is the additive manufacturing. Additive manufacturing is an essay assignment. Okay. Any other questions? Tak ada. Okay. If no questions, basically there's also attached video that you should look through, that you should have looked through already, and also there's a quiz. So please attempt the quiz. I'm going to open it until I think Thursday evening. So you have from now until Thursday evening to attempt it. Then on Friday, I'm going to take the attendance based on that. Any questions?
No, sir.
No, sir.
No, sir.
Okay, if no questions, I'm going to stop here. So kita punya apa ni? Kita punya ni pun has been extended for until June. So so you should expect final exam will be open book exam. So open book exam ni you browse lah dekat online, tengok apa dia criteria and characteristic of the open book exam ni. So it will be what you have to deal with to answer those questions. Okay, so kalau
Yes, sir.
kalau tak ada apa pertanyaan, then thank you very much. Selamat puasa dan selamat berbuka semuanya. Stay safe. Okay. So, Assalamualaikum.
Alright, sir.
Okay.
Thank you, sir.
Salam.
Thank you, sir. Waalaikumsalam.
Thank you, sir.